Hello, class. We're about to start lesson 4-1. So you're saying there is a chance, and this is on page 365. Our learning objectives is to understand key terminology in the study of probability, and then to compute and interpret theoretical and empirical probabilities, and to compare theoretical and empirical probability. A scientist worthy of a lab coat should be able to make original discoveries while wearing a clown suit, or give a lecture in a high, squeaky voice from inhaling helium. It is written nowhere in the math of probability theory that one may have no fun. That is Eliezer Yudkowsky. Okay, let's look down here at the bottom. It says, in this lesson, we'll examine the basic concepts involved in studying probability. In short, the probability of something occurring is a number that represents how likely it is to occur. You could think of it as the percent chance of something happening. The major difference between percent chance and probability is that we write probability as a number between 0 and 1. So in that regard, it's like percent chance with the percentage written in decimal or fractional form. Number one, a forecaster says that there's a 70% chance of rain today. What is the probability of rain? So if it's a 70% chance of rain, we know that 70% is written like this as a percentage. So that's 70%. So the probability is 0.7, or you could write it as a fraction as 7/10. So this is the probability. As remember, probability is written as a decimal or a fraction, not as a percent. So now we go right here to the back. It says here sample spaces. Processes such as flipping coins, rolling dice, or drawing cards from a deck are called probability experiments. A probability experiment is a process that leads to well-defined results called outcomes. An outcome is the result of a single trial of a probability experiment. Let's illustrate our terminology. Flipping coins is an example of a probability experiment. One flip is a single trial of that experiment, and having the coin land tails up is an example of an outcome. In a probability experiment, we can predict what outcomes are possible, but we can't make any definite statements about which one will occur for any given trial. We say that the outcomes occur at random. In any probability experiment, the set of all possible outcomes is called the sample space. Okay, now we have to solve example one. It says finding the sample space for a probability experiment. It says list out the sample space for each probability experiment. So we have flipping a coin, rolling a standard die, answering a true or false question, and flipping two coins. Now, we're provided with the solution here. It says in each case, our job is to make a list of all the things that could possibly occur for the given experiment. When a coin is flipped, it either lands heads or tails up. So the sample space is, you notice here we have braces and heads, comma, tails. A standard die has 6 sides, numbered from 1 to 6, and each number can be rolled. The sample space is, you notice here that it's in braces and it's number 1 through 6. This could be interpreted in a couple of different ways. There are two possible answers, so the sample space could be true, false. You could also consider that every answer is either right or wrong and write the sample space as right or wrong. The key here is to think of the experiment as a sequence of two flips. You could get either heads or tails on the first. Then once you know what came up first, you could also get heads or tails on the second. So the sample space is head, then heads, then tails, tails, then heads, tails, then tails. Okay, so with that being said, I'm going to write out the sample space because typically we do not write the word then. So I do a brace here and it says head, then heads. So then I put HH for two heads. Then we had heads, then tails. We had HT. Tails, then heads, which would be TH. And then finally tails and tails. These are the sample spaces written out. Okay, now number 2. It says write the sample space for the probability experiment of identifying a student's grade in a chemistry course. Okay, now depending on what school you go to, typically most schools that I've encountered typically give an A, B, C, D, or F. Now we're not talking about incompletes or anything like that, but strictly letter grades. So we could say our sample answer would be A, B, C, D, F. Now, it says here, when studying probability, it's pretty common to think about several outcomes of an experiment that are related in some way. For example, when rolling a die, we might be interested in whether the result is odd. Okay, now it says write all outcomes of rolling one die that are odd. So remember, dies go from 1 through 6. Now, I'm going to write the sample space here. You don't have to do that, but we could look at the sample space. This is a sample space of a die, and they want us to do all odd. So it's 1, 3, and 5. So your answer here would be 1, 3, 5. You just wrote an example of an event. An event is a collection of one or more outcomes in a sample space. Some events, like rolling a 3 with one die, have only one outcome. Others, like rolling an odd number, have more than one outcome. There's a subtle distinction between an outcome and an event. An outcome is a single occurrence, while an event can contain a number of outcomes. So rolling 3 with a single die is an outcome, but can also be considered an event. Rolling an odd number, on the other hand, is an event made up of 3 outcomes, but is not itself an outcome. Let's look at that distinction more closely. Look back at the sample space for flipping 2 coins and solve example 1. How many results match getting heads on the first flip and tails on the second? Okay, so if we look back here on the previous page, I wrote out the sample space. They said heads on the first, tails on the second. So with that being said, we only have 1. So it'd be just 1. Now, that's an outcome. How many results match getting 1 head and 1 tail? Now it says 1 head, 1 tail. They are not asking us a particular order. So 1 head, 1 tail, both of these. So it's 2. So we will write 2. That's an event. Identify each scenario in questions 6 through 8 as an event, an outcome, or both. When rolling 2 dice, getting 3 on the first die and 5 on the second. All right, this is an outcome. It is a single occurrence. Now we can say it's an event as well. We could say it is an event as well. Okay, now when rolling 2 dice, getting a total of 10. Now, This is just an event because there is more than one way to get 10 rolling 2 dice. When flipping a coin 10 times consecutively, getting tails 8 times. Okay, this is an event because there are more than one way to get tails 8 times. Now, I would just verbally say this. You could roll tails 8 times in the first 8 flips, or you could roll tails 8 times in the last 8 flips, or you could roll 8 tails in the middle 8 flips, or you could roll 8 tails, you know, yeah, with consecutively, yeah. So those are examples there that will show that you could get tails 8 times multiple ways. All right. Now we come here to page 369. It says, wait a minute, I'm sorry, I skipped 368. Okay, now we come here to theoretical probability. It says, now we're ready to specifically define what is meant by probability. The first type we'll study is called theoretical probability. The goal is to identify all of the possible outcomes in a sample space and calculate the probability or likelihood of an event occurring without actually performing experiments. There is one key assumption we make in theoretical probability, that every outcome in a sample space is equally likely. For example, when a single die is rolled, we assume that each number is equally likely to come up. When a card is chosen from a deck of 52 cards, we assume that each card has the same probability of being drawn. Number 9, you'd have to be awfully bored to flip a coin 100 times. But if you did, about how many times do you think it would land tail sides up? Now, of course, the answer is going to vary, but if this is a fair coin, we would assume 50 times. 50 times for heads, 50 times for tails. Now, number 10. What percentage of the time would you expect the coin to land tails up? Be 50%, because it was half. All right, 11. Write a fraction with the number of flips in the denominator, which we know would be 100, and the number of times you're expecting it to land tails up in the numerator, which would be 50. What does this have to do with your answer to question 10? So basically, this provides the percent or the percentage of number 10. Okay, next. It says, congratulations. You've just computed your first theoretical probability. You didn't actually flip a coin 100 times. You just used reasoning ability to decide what the likelihood of getting tails is. That's what makes it a theoretical probability. You develop a theory by thinking, as opposed to gathering data experimentally. We'll get to the experimental part in a bit. Okay, so now calculating the theoretical probability, we have the probability of the event is the number of outcomes in the event divided by the number of outcomes in S, and S is your sample space. Now, for questions 12 to 14, a single six-sided die is rolled. Find the probability of each event. If you need to, look back at the sample space from solved example 1, part B for reference. Okay, rolling a 2. Now, I'm going to write the sample space here. This is the sample space for a die, 1 through 6. So rolling a 2, 2 only appears 1 out of 6. So writing this out, the probability of the event, the number of outcomes, I'll put in, number of outcomes for the event, and the number of the sample space. Now the number of the sample space was 6. The number of the event occurring is 1. So your answer here is 1, 6. So your PE is 1, 6. All right, now we move on to page 369. It says rolling a number less than 5. Now you can refer back to that. Well, let me see if I can pull this up here. Just looking at the sample space. It says rolling a number less than 5. We look at the numbers less than 5 is 4. But remember, we have n of the event and n of the sample space. All right, now we know the sample space is 6. And the event happening, numbers less than 5 is 4 of them. So it's 4 or 6, but you can simplify down to 2/3. So the probability of the event is 2/3. Now 14, it says roll in an odd number. So the probability of the event, we know the sample space is still 6. And the odd numbers are 1, 3, and 5. So that's 3 out of 6, which is 1/2. So the probability of this event is equal to 1/2. All right, now, look here, number 15. If 3 coins are flipped, write the sample space. Remember that tails, heads, heads is a different outcome than heads, heads, tails, even though both result in 1 tail and 2 heads, which, by the way, sounds like a, yeah, okay. Anyway, all right, so we want to look at this. We flip 3 coins. So we know with 1 coin, we can get all tails. Another coin, we could get, well, another flip, we could get 2 tails and a head. We can get a tail and 2 heads. We can get a tail, a head, and a tail. We can get a head and 2 tails. We can get a head, a tail, and a head. We can get 2 heads and a tail. And then we can get 3 heads. So we actually have, what, 8 outcomes, or 8 for our sample space. Now, it says for questions 16 through 18, 3 coins are flipped. Find the probability of each event. So we want 2 tails. They didn't say in any particular order. So if we look here, we have 2 tails in 1, 2, 3 areas. So remember, our probability of the event, the number in the sample space is 8, and then we have 2 tails 1, 2, 3 times. So it'd be 3x. Now, 17 said at least one tail. That means that it must have one tail or more. So when we count this, it's the probability of the event. We know it's 8 in a sample space. So now we go here and see all the ones that have at least one tail. 1, 2, 3, 4, 5, 6, 7. So it'd be 7 out of 8. Because this is the only one that don't have at least one tail. Now it says at most one tail. So that means it could only have one tail or less. But remember, our sample space is still 8. And so one tail or less. So we have 1, 2, 3, 4. So that'd be 4 over 8, which is 1/2. So the probability of the event is 1/2. Okay, now we move on over to the next page. Now with this next page, basically you could read this at your leisure where it says describing properties of probability. So basically it says probability can never be greater than 1 or less than 0, which is a true statement. If it's 0, that means it cannot happen. If it's 1, that means that it'll happen all the time. It's a guarantee. Probability is 1 when the event is certain to occur and 0 when the event can't occur. And that's true as well. See, if you add the probabilities for all outcomes in any sample space, the result has to be 1, which is also a true statement. Because remember, all of those are fractional parts. And just like with the going back to the dice example, if you look here, all of these, if you count them, this would be 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, and 1, 6. Because all of them is 1 out of 6, and that will equal to 6, 6 once you add them up. So that is a true statement as well. So we are done with 4.1, and now we're going to go over to 4.4. Okay, class, lesson 4.4 starts on page 425, and it's called Crunching the Numbers. Our learning objectives is to explain the difference between a population and a sample, to compare and contrast different sampling methods, to organize data with frequency distribution, and analyze data with stem and leaf plots. So we have quite a bit to do with this lesson. So it says errors using inadequate data are much less than those using no data at all. Charles Babbage. Okay. As we began our study of statistics, it would seem reasonable to have a really good idea of what that actually means. Statistics is a branch of math that involves collecting, organizing, summarizing, and presenting data and drawing general conclusions from those data. If we're talking about grade inflation, then relevant data must be average grade point averages for students in several different years. The table below shows some GPA data from the website gradeinflation.com. And you see here, we go from 1983, looks like we're going intervals of 5 years all the way up to 2013. Now, it says here, in statistics, we start with the question we like to answer, like, is grade inflation a real phenomenon? Then we gather data and try to interpret them in order to answer the question. It sounds reasonable enough. All right. Write a verbal description of the information provided in the table. Do you think it supports the idea of grade inflation? Okay. This is average GPAs have been going up every 5 years. The increase in each 5-year period was at least 0.04 and at most 0.07. GPAs have went up, but the numbers don't say the grades are inflated. There's nothing in the numbers that support that. It says, how do you think these numbers were calculated? What student GPAs were considered? Well, there's a lot of things that could have happened here. They could have considered, because it doesn't, as far as I know, it doesn't tell us what students that they included. It could have been the top students of the school. It could have been a select type of schools. Like there are some schools that only let high achievers in. Or it could be these numbers could have been calculated taking out certain courses. We just don't know. So that is up to your discretion. It says the ideal way to gather GPA data would be to add the GPAs of every college student in America during each year, then divide by the number of students. Needless to say, that's not particularly realistic. Aside from legal ramifications, in any given year, there are more than 20 million students enrolled in American colleges. And by the time all that GPA data were gathered and recorded, many of them would be contemplating retirement. Instead, GPA data are obtained from a sample of college students. Okay, now it says a population consists of all subjects under study. A sample is a representative subgroup or subset of a population. In the case of the GPA data we've been studying, the population it'll be every college student. The sample is the group of students whose GPA were included in the averages. In this case, GPA data from a sample of 70 different colleges were used to compute the average. The thing that makes the data compelling is that the sample is representative of the population as a whole. The schools chosen vary in size, cost, and geographical location. Some are public, some are private. Discuss what exactly is meant by a representative sample and why it's so important in answering questions using statistics. Basically, when you're talking about a representative sample, you're talking about a sample or a group of students that represent basically a vast majority of different types. Like we have public schools, we have representatives from private schools. We um, we had schools that were large, we had schools that were small, we had schools that were ultra expensive, and we had schools that were fairly cheap. So that's basically what a representative sample is. You took, you know, a sample from those different aspects of each school. All right. So now We move on to sampling methods. It says we will study 4 basic sampling methods that can be used to obtain a representative sample: random, systematic, stratified, and clustered. In order to obtain a random sample, every subject of the population has to have an equal chance of being selected. The best way to obtain a random sample is to use a list of random numbers. These can be generated from a variety of internet sources or from a computer or calculator. Subjects in a population are numbered, and then the ones to be studied are picked by using the corresponding random numbers. If you are going to do a survey with every student at your campus as the population, describe how you might obtain a random sample to survey. More specific is better. We could use student ID numbers and have a computer choose random numbers from that list. A systematic sample is taken by numbering each member of the population and then selecting every kth member, where k is some natural number. For example, the researcher from gradeinflation.com might have numbered all of the colleges willing to release grade information and chosen every 10th one. In this case, k is 10. When using systematic sampling, it's important that the starting number is chosen randomly. Let's get back to the campus survey mentioned in question 6. Describe how you might develop a systematic sample. So basically, we can use student IDs, student ID numbers, then choose every 10th or every 100th or something like that. Now, when a population is divided into groups where the members of each group have similar characteristics, like large public schools, large private schools, small public schools, and small private schools, and a certain number of members from each group are chosen at random, the result is called a stratified sample. For example, the grade inflation researcher might have decided to choose 5 schools from each of those groups. Medical researchers often stratify samples by dividing subjects into gender groups, age groups, racial groups, or many other categories. They would then randomly choose a similar number of subjects from each group to compose the stratified sample. Describe how you put together a stratified sample for that campus survey we've been talking about. We could divide students up by class standing. Now, when I talk about standing, I'm talking about whether they're freshman, sophomore, junior, or senior. Then choose the same number of students from each class. Okay, now we're going over here to page 428. It says when the existing group of subjects that represent the population is used for a sample, it is called a cluster sample. For example, suppose we were interested in studying hunger in Ohio. There are 88 counties in the state, so we could randomly pick a dozen of those counties. We could then choose a random sample of cities in each selected county to gather data on the number of food insecure families in those cities. In the case of the grade inflation study, researchers might look for existing groups that colleges fall into. There are several different organizations that provide accreditation to colleges in the United States. If a couple of those organizations were chosen randomly, then schools from each of those groups could be surveyed for GPA data. The accreditation organizations would be the clusters. It can be a little tricky to distinguish between stratified and cluster samples, so you might find it helpful to think of it this way. If the entire population is divided into distinct categories and some subjects are chosen from each category, that's a stratified sample. If the subjects are chosen from just a small handful of existing groups, that's a cluster sample. Describe how you might develop a cluster sample for our campus survey. Okay, you probably could take students taking a particular course in a certain major or in a particular student organization. Now, it says think about 4 different sampling methods the researcher from gradeinflation.com could have used. For questions 10 through 13, write each of the sampling methods we've studied was used for each situation. Explain your choice. The researcher randomly selected 3 states and then asked all colleges willing to release grade information from those states. That is a cluster sample. The states are the clusters. All right, number 11. The researcher numbered all of the colleges willing to release grade information and chose every 10th one. That is systematic or a systematic sample because every 10th school was chosen. Now we come here to number 12. It says the researcher numbered all of the colleges willing to release grade information and chose several of them using a random number generator. So this will be a random sample. There was no order for the assigned number, just a random group chosen. 13. The researcher grouped the school by 2-year state schools, 4-year state schools, 2-year private schools, and 4-year private schools. The researcher then decided to choose 5 schools from each of those groups. That's a stratified sample. The key is that a certain number of schools were chosen from each category. It says rank the 4 sampling methods in questions 10 through 13 from best to worst in terms of how representative you think the sample would be. Explain your rankings. Now, this is a personal choice, so I'm not going to write out a ranking because your ranking might be different from mine. This is all up to you. This isn't a right or wrong answer. So you can rank them however you think which one would be the better. Okay, now we move on over here to page 430. It says frequency distributions. The data collected for a statistical study are called raw data. Raw data can be really difficult to interpret in order to describe situations and draw conclusions. We need to organize the data in a meaningful way. 2 methods that we will use are frequency distributions and stem and leaf plots. First, we'll study categorical frequency distributions, which are a way to organize data that are divided into distinct categories like gender, your class standing in school, or conferences for college football teams. A categorical frequency distribution is a table in which you list different categories. Then count up how many individuals in a sample or population fall into each category and list those frequencies. In questions 1 and 2, you'll create a categorical frequency distribution. Number 1, it says 25 volunteers for a medical research study were given a blood test to obtain their blood types. The data are shown below. What would the categories for these data be and why? Okay, basically, it will be the blood types. It will be the blood types because these can be divided up into their distinct categories. And this is the data that we're talking about. So number 2, it says build a categorical frequency distribution by writing in your categories, then putting tally marks in the second column as you count the number of individuals in each category. So if you look here, we have blood type A, B, AB, and then O. So we do our tally marks here. If we look at A, we have 1, 2, 3, 4, 5 for A. And then B, well, I guess I should do it since I see 1 there, another one, 2 more, then another one, and another one. So I have a total of 7. AB, we have 1 here, 2, 3, so it'd be 4. Then finally O, we have 1, 2, 3, 4, 5, and then 6, 7, 8, 9. So we have 9. All right. It says use your distribution to write some conclusion on blood types in the population. Do you think that there's enough data for your conclusion to be reliable? Okay, first of all, we could say that according to our frequency distribution most people have O as their blood type, and AB has the least amount in this blood type. Okay, there are over 6 billion people in the world. So a sample of 25 is not enough to draw a conclusion. There's over 6 billion people in the world. I would not trust my conclusion to that of just 25. That's not enough. Okay, now we move on to the next page. It says another type of frequency distribution that can be constructed uses numerical data and is called a group frequency distribution. In a group frequency distribution, the numerical data are divided into classes. For example, if you gather data on the weights of people in your class, there's a decent chance that no two people have exactly the same weight. In that case, everyone would be in a separate category, and each category will have one weight in it. This, of course, would make the frequency distribution no more useful than the original list of raw data. So it'd be reasonable to group people into weight ranges, like 100 to 119 pounds, 120 to 139 pounds, and so forth. In the 100 to 119 pound class, we call 100 the lower limit and 119 the upper limit. With these ranges, where would we put someone who weighs 119.8 pounds? It'll be nowhere, which would be a problem. All right, the reason why is because we had 100 to 119, then we jumped to 120. There are values in between the 119 and 120 that we're not accounted for. So that is why we put nowhere. As question 4 illustrates, the way we choose classes is dependent on how the data values are rounded. The weight classes we choose earlier would be fine if all the weights were rounded to the nearest pound. But if weights were rounded to the 10th of a pound, we want to make the classes 100 to 119.9 and so on. Now it says constructing a group frequency distribution. First, you have to decide how many classes you want to divide the data into, and you have to choose between 5 and 15. Number 2, determine the width of the class. So you'll take the largest data value minus the smallest data value divided by the number of classes. Then round this value up to the next biggest whole number. So even if you ended up with 5.01, it still will go up to 6. So just to let you know what they mean by the rounding. It's not the typical rounding rule where you look for the 5 and that tells you to round up or leave it the same. No, what you look for is whatever that number is in front of that decimal, you just add 1 to it and that will be your number. Okay, now, step 4, add the class width to the first lower class limit to get the second lower class limit. Do this for all classes. Oh, I skipped step 3. It says use the lowest number in the data set or a nice number lower than that number for the lower limit of the first class. Add the class width to the first lower class limit to get the second lower class limit. Do this for all classes. Find the upper class limit for each class by subtracting 1 from each lower class limit. And finally, step 6, tally up the number of data values in each class, then put the frequencies next to each class in a table. All right. Now we come here to the back. It says we'll illustrate by organizing the following data, which are the record high temperatures for each of the 50 states in degrees Fahrenheit. So we see all of those different degrees that we have here. It says, why would a categorical frequency distribution be a bad idea for these data? Hint, what would the categories be? Individual temperatures would be the categories. Data values range from as low as 100 to as high as 134. So there would be 20 or more categories. Now remember, earlier we said that for the categories, we should only have like 5 to 15. So this is saying we would have 20. So that's what makes it, a bad idea for that frequency distribution. Now it says building a group frequency distribution. It says organize the record high temperature data from the table into a group frequency distribution. So we go through each one of the steps. So basically, we first find the class width, the largest value, which is 134, minus the smallest value, divided by the number of classes, because we're going to try the number of classes at being 7. So 134 minus 100 is 34, divided by 7 is approximately 4.9. So rounded up, we find that each class will cover a range of 5 degrees. Okay, now it says here, decide on a lower limit for the first class. The lower data value is 100, and if we start there, our classes will have nice, easy boundaries. So let's do it. Now, if you look at step 4, find the lower limit for all the other classes, starting at a lower limit of 100 and adding the class with 5 repeatedly. So we get 100, 105, 110, 115, and so on. And then it says find the upper limits for each class. What we could do is this here. You could just subtract 1 from here. That'll give you 104. And then you could just keep adding 5, which is the class width. Once you get that first value, then all you have to do is add the class width. Says set up a table and build the group frequency distribution. We set up the table with the class limits that we chose, then go through the data values one by one. Put in a tally mark in the appropriate class for each value. Finally, we add the tally marks to complete the distribution, which we show here. Now, it says write down at least 3 observations you can make from analyzing your frequency distribution. So first of all, we could say extreme temperatures are the least amount of occurrences. Because we look here, the 130 to 134, the 125 to 129, and the 100 to 104. All 3 of those are the the lowest outcomes. They said 3, so that's 1. Number 2, the larger outcomes are the temperatures in the middle. Number 3. See, with number 3, I probably would say that that the pattern seems to increase, then decrease as temperatures continue to rise. All right, now we'll go on to page 434. It says the data below represents the team record for Twins in a single season by all current Major League Baseball teams. Organize the data into a group frequency distribution. Okay, first of all, we need to look at the class width. So we take the largest data value. Let's see, what is the largest data value? It looks like 116 is the largest data value. So I'm going to put CW for class width. The large data value is 116. The lowest data value, it looks like it is 92. Now we know we need to divide by the number of classes we want. But first, let's take this 116 minus 92. That looks to be about, what, 24? Now, if we think about it, remember we want classes, it's like 5 to 15. Now, we got the number 24 here. We could pick a number that would evenly go into 24. Or we could pick something a little outside of the scope. Because if we pick 6 would go into 24. And then our class length would end up being just 4. So I think we should do 7. I think we should have 7 classes. 24 divided by 7, we know it's going to be 3 point something. So let me type that in. 24 divided by 7 is 3.42. So we could say approximately 3.42. And then we will round that to 4. Because remember, we will go up. So that means our width is 4. So now we could do, that's a quick table here with the class and then the frequency. So let me see, it's supposed to be 7 classes. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Okay, so we have our 7 classes. Now, we could start off with the 92, and then we could add our class width down. So that'll be 96, 100, 104, 108, 112, 116. Now that's our lower limit. Now to get our upper limit, we'll go to the second value here and subtract 1. So this would be 95. Now, once we get this 95, we could just add the class width to it. So it'll be 99, 103, 107, 111, 115, and 119. Now, when we go through and count here, we will end up with 2, 6, 7, 6, 6, 1, and 2. Now, you could take the time out and count it, but this is one of the answers here. Now, of course, if you use a different width of classes, you could have used 6. As long as you're in between that 5 to 15 range and you count it up properly, you should be fine. Okay, now it says once we've organized data into a group frequency distribution, we might find it useful to illustrate those data graphically using a histogram. A histogram is similar to a vertical bar graph in that the heights of the bars correspond to the frequencies. There are a few differences, however. First, the width of the bars has meaning. It's representative of the class width. Second, the bars are drawn right next to each other with no space in between them. Finally, the most important difference is that the boundaries of the classes are placed on the horizontal axis rather than the name of the categories. Okay, now it says, write the scale for the frequencies on the vertical axis and the boundaries of the classes on the horizontal axis. Put label tick marks at the lower boundary of every class. Okay, K2, draw vertical bars with heights that correspond to the frequency for each class. When drawing a histogram, make sure that there is no horizontal space between the bars, unlike a bar graph, unless two bars are separated by a class with frequency 0. Also, make sure that all classes are included, even if the frequency is 0. Okay, now, it says here, let's walk through an example of drawing a histogram that illustrates the high temperature data, which was arranged into a group frequency distribution, and solve example 1. On the axis below, label the horizontal axis by marking off all of the lower class boundaries from the frequency distribution on page 433. Hint, it would be a good idea to label the very beginning of the horizontal axis where it meets the vertical axis with 95. Okay, now, if you go back to the temperatures, I believe, okay, the temperatures start at 100. So they wanted us to go a little lower than that. All right, so yeah, a little lower using the class width, because remember, with the class width, you'll keep adding that down to the lower limit. So if it's 95 and you add 5, that'll give you 100 and so on. Okay, so now we want to label this graph. So we make this 95, and then this will be 100, 105, 110, 115, 120, because they want us to get the lower limit, 125, 130, 135. And technically this would be 140. All right. Now off to the side here, the number of states, we'll start off with 0. And then for the number of states, we could go 2, 4, 6, 8, 10, 12, 14, 16, 18. Because it's doubtful that we would get that many states that have the same temperature, but it's good just to go there just in case. All right, so for 100 to 105, we actually, did have the table done for us here. It's really 100 to 104, which should be 3, because this right here, 105, only starts when we go towards the 110. So that's one other thing you need to know. So from 95 up until 100, there's no line there because nothing is shown. So now 100 to 105, based upon here, that'll give us 3. So we will go 2, and we'll go to the halfway mark. So that's 100 to 105. Then 105 to 110, which would be 100. 109 would be 8. So we'll go up here to 8. And then next, from 110 to 114, or in this case, the 115, we would have 16. So what we would have to do is go up to the 16, draw it here, and come down here to the 115. I'm actually a little off. It should be directly on that line there. Yeah. All right, next, 115 to 119 is 13. So we would go here. And then, what's that? 120 to 124 is only 7. And then 125 to 130 is 2. And then finally 130 to 134, which would go here. Oh, you know what? I skipped right in 130. How did I do that? Okay. So that's 130. Now we will go from 130 to 134, which will only be 1. So that'll be like the halfway here. Then it's nothing for the 140. All right. Oh, actually, I actually did 9, 10, and 11. I drew all of the bars and everything. So that basically is 9, 10, and 11. So, okay, so now we move on to page 436. And it says here, another way to organize data is to use stem and leaf plot, sometimes called a stem plot. Each data value or number is separated into 2 parts. For a 2-digit number such as 53, the tens digit 5 is called the stem and the ones digit 3 is called the leaf. For the number 72, the stem is 7 and the leaf is 2. For a 3-digit number, say 138, the first 2 digits, 13, are used as the stem and the third digit, 8, is used as the leaf. For values rounded to the tenths place, like 8.4, you can use the value to the left of the decimal place as stem and the tenths place as leaf, as in our next example. In any case, the very last digit is used as the leaf and what comes before as the stem. Note that we'll include a key with our plot that clarifies what the stems and leaves represent. The following data are the January 2019 unemployment rates for each state. Okay, now, what happens here is, down here at the bottom, they actually show us with the solve example 2 about the stem and leaf plot. Okay, now it says draw a stem and leaf plot for the unemployment data provided. The logical choice of stems here is the digits in the ones place, because as you notice here, in front of this decimal, we just have the ones place. It'll just be the ones place. Okay, Notice, well, the ones place and the leaves will be the digits in the tenths place. Notice that the digits 2, 3, 4, 5, and 6 appear in the ones place. So those will be all the stems. We then go through the data one by one and write the leaves next to the appropriate stem. So basically, we're writing out these values. If you notice, there's no commas separating these numbers. That's because when you do a stem and leaf plot, it's assumed that those numbers are the last digits of that number. So you do not put commas in between those numbers or it is incorrect. And then here they put the key, 6 as the stem, 5 as the leaf, meaning 6.5. And all of these will line up to the values on this table. Okay, now we go here to the top. It says solve example 2, continue. Notice the key at the bottom. This is really important for letting the reader know exactly what the stem and leaves represent. There's nothing wrong with our plot at the moment, but to make it a bit more organized, it's customary to rearrange the leaves by increasing order. So our final plot looks like this. So basically what they're saying here is, on the bottom here, they listed the numbers as they appeared. So you notice the leaves are out of order as far as the numerical order from smallest to greatest. So what they did here was organize the leaves from smallest to greatest. So it didn't change how many you had at 2.4 or anything like that. Now, one other unique thing that you need to see here is we did have some values here that were exact, like no decimals or whatever. So we have 4 and 3. So if you look here, you have some zeros here. That's what represents the tenths place that was not added there. So that's like 3.0 or just 3. Okay, now it says write at least 3 observations about the unemployment data from looking at your stem and leaf plot. Okay. Well, if we look here, extreme values are fewer than the middle values. Extreme values are fewer than the middle values. So that'll be 1. Number 2, the 3 range, I should say 3 and 4 range. The 3 and 4 range for unemployment is the highest. Okay, number 3, and remember we're talking about frequencies here. When I say extreme values are fewer than the middle values, I'm talking about the frequency. The 3 and 4 range for unemployment is the highest. I'm talking about frequency because we know 6 is higher than 3 and 4, but as far as the frequency is more of 3 and 4 than it is of 6. And then they said the third observation, well, we could say more states are in the 3 and 4 range than any other range or frequency. Okay, now we come down here to the bottom. It says deciding on stems and leaves for the unemployment data was fairly simple because there was a natural choice of stems, the whole number part of each rate that gave us a reasonable number of them, 6. That's not always the case. For the high temperature data earlier in this lesson, the natural choice of stem would seem to be the first two digits. But here's what the stem and leaf plot would look like in that case. Okay. Now explain why this stem and leaf plot isn't really very helpful in organizing the data. That is because there are not enough categories. There's not enough categories. Now we come here. It says, in general, it's a good idea to choose stems so that there are between 5 and 15 categories. In the case of the high temperature data, we get a better organization if we divided the categories in half so that the first category covers 100 to 104, the second 105 to 109, and so on. To signify this, we can use the symbol 10 0 to represent a stem of 10 with leaves that are digits from 0 to 4, and 10 5 to represent a stem of 10 with leaves that are digits from 5 to 9. Complete the stem and leaf plot for the high temperature data on page 432. We've helped you start by including the first 4 stems. Don't forget to include a key. All right, so we will go here. We will have to do 12 0, 12 5, and then 13 0. Because remember, we go up to the 130s. So now, our leaves here, we will add 0 0 4. For the 5, we will have 5 5, 6 6, 7, 8 9 9. 11 0, we will have 4 zeros, a 1, 4 2s, 3 3s, and 4 4s. 11 5, we had 2 5s, a 6, 3 7s, 6 8s, and 1 9. Now 12 0, we will have 4 zeros, 1 1 2. 12 5, we will have a 5 and an 8, and 1 3 0, we will have a 4. So if we did a key here, we could take one value like 10 0, and then we could do a slash, and then we could say 4. 10 0 4 means 104. And then 10 5 of, let's see, 7 means 107. All right, 15. It says, describe why this stem and leaf plot makes it easier to analyze the organized data than a preceding one. With more categories, we can see the largest number of states with high temperatures For example, instead of 110 to 119 having so many values, we can see that 110 to 114 is larger than 115 to 119. Okay, now 16. It says compare group frequency distribution and stem and leaf plots. How are they similar? What do you think makes it easier to analyze a set of data? Now, of course, this is your opinion, and I would just say this. As far as what makes them similar is that you're organizing the data and you could actually see, like in a certain group, how many that you have in that certain group. But the big difference between the two, and I would stress this, the big difference between the two is in stem and leaf plots, you could get all the exact answers out of that. But with group frequency, you don't know. Like if you put in that it was 5 that fell in between 110 to 119, you don't know what 5 it is. It could be 5 111s, or it could be a 111, 112, 113, 114, 115. We don't know. But with the stem and leaf plot, we can easily look and then we can easily see what the numbers are. So that is the big difference. And we're done with 4.1 and 4.4.